Hello everyone and welcome back to this NPTEL course on aquatic geochemistry. Today is the 17th lecture and we have been discussing a bit about thermodynamics and how it is helping us understand the composition of natural waters. So, in our last lecture I gave you one example where as an environmental geochemist you are supposed to find the solution for a place which is affected due to mining, okay, and the stream was contaminated, and we can use our thermodynamics to understand certain basic reactions that is going on in that area and how it is going to change the water composition of the stream and of the estuary. Okay. Let us look into some more examples and then I will go on explaining what kind of calculations that we do with our thermodynamic knowledge. Okay. Another very important example is related to complexation. Okay. For example, iron is a very essential micronutrient. Okay. And often it is seen as the limiting micronutrient in the oceans where there will be this high nitrates, but you will see that the chlorophyll content is very low. That is because iron in those waters is not sufficient for the growth of more microorganisms. Okay. So, even though nitrogen is available, phosphorus is available, iron is not available. Okay. So, what as a solution now you see there is a lot of methods that people are thinking to bring down the carbon dioxide concentration in the atmosphere. We want to reduce climate change and the gas that is causing all this global warming. One of the most important, as we have all the studies have pointed out, is the higher amount of carbon dioxide in the atmosphere due to this industries and agricultural practices. So, basically after the industrial revolution, the carbon dioxide in the atmosphere has jumped up, okay, it has spiked, and that has caused global warming, and I think in all over the globe we are seeing its impact in some form or the other. Okay. Now, to bring down that carbon dioxide level, multiple methods are being sought after. Okay. And one of the methods that was tested is whether if we fertilize the low low iron areas in the ocean artificially with iron, then can we increase the primary productivity of that area, and if the primary productivity increases, of course there will be more carbon drawdown. Okay. So, basically we want to increase the primary productivity in the ocean, and since iron is the limiting micronutrient, we have to supply iron artificially. Okay. Now, to conduct this successfully, few important things has to be determined. First of all, what is that iron form that is uptaken by the phytoplankton? And it is found that Fe3 plus is the form which is uptaken by the phytoplankton. Okay. So, we should know that if we are fertilizing the iron, it is there as Fe3 plus in the dissolved state and not getting precipitated out. See, if I am fertilizing the ocean and it is not dissolving, it is just getting settled down, then there is no use, so the experiment will fail. Okay. So, we have to make the iron such that it is available for the phytoplankton to be uptaken. Okay. So, we have to find out what is the activity of the free Fe3 plus. Okay. So, if I am throwing 1000 kg of iron, okay, not necessarily all the 1000 kg will be dissolved. of course a certain fraction only will be dissolved. Okay. Now therefore, what is the success rate will be determined. If I see only a very minor fraction is getting dissolved, the rest is all just getting precipitated out, then there is no point making it is in a economic large scale. You cannot do that, okay, activity. So the feasibility will be low for such experiments. Okay. So we have to find out from our calculations that what reactions will favor for Fe3 plus to be there, and how different organic and inorganic ligands can change that composition. Okay. So here is our main two question. Okay. First thing, what reactions are going to make Fe3 plus in the water, what reactions are going to allow Fe3 plus to remain in the water, okay. And mostly there is hydrolysis going on, okay, and speciation is happening. Okay. What speciation reactions are happening, we need to check that, and interaction with inorganic and organic ligands. Now what are ligands? Ligands are particular molecules, or it can be atoms also. Okay. So atoms or molecules that is interacting with a particular metal. Okay. It can be of organic in nature, it can be of inorganic in nature. Okay. For example, the most common inorganic ligand is OH minus. Okay. And organic ligands can be extremely complex. Okay. There can be different carbohydrates, they can be in terms of different protein molecules. Their complexity is as variable as the organic matter is variable. Okay. Now these organic ligands, they attract the Fe3 plus and they form these complexes. So generally metals, they are always not available in this free ionic forms. They are always certain metals are there more in as complexes. Okay. Their solubility also increases if they are in certain types of complexes as compared to their free ionic form. Okay. So we will first of all write the hydrolysis reaction, that is Fe3 plus H2O will form FeOH2 and that will be plus H plus. Okay. So then certain reactions with the ligands, okay. Organic complexation with siderophores. What are siderophores? Siderophores is a type of organic molecule that has a very high affinity for Fe3 plus. Okay. It is basically exuded by a certain type of microorganisms. This attracts the iron, okay, and then it provides it to that microorganism. So single celled organisms and certain multicellular but lower life forms, their assimilation types are very different. Okay. So they do not have the complex systems like we humans have or the higher life forms have. So they will to provide them their basic micronutrients, they will produce certain types of enzymes or molecules such as siderophores, which will attract that particular element and will provide it to them. Okay. So if we know the concentration of organic ligands and their binding constants, we can start writing this equation and see how much of it will be available. Okay. Another example, okay, carbonate formation, calcium carbonate formation in marine sediments. Okay. Now calcium carbonate is present in shallow sediments, but as soon as we go deeper, okay, in deeper oceans, we do not find it. Okay. So beyond a certain depth, calcium carbonate is not found. Okay. So question arises, is this depth controlled by mineral solubility? Okay. Now saturation, okay, of calcium carbonate, whether okay, after beyond a certain saturation it will start dissolving, or again it starts getting undersaturated, so again it starts dissolving precipitation. So, all this dissolving precipitation reaction depends on the saturation level, right, and that is a function of temperature and pressure, and that can be calculated using thermodynamics, right. So, the equilibrium constants, which is a function of temperature, pressure, and since it is happening in the ocean, therefore, salinity, okay, the presence of other constituents is important, okay, and we have to write down all the solubility reactions. For example, the very basic one, that is calcium carbonate, if it is dissolving, it will form calcium iron as a calcium ion and carbon dioxide. Okay. So, either that carbonate is getting released as a anion and it can again break down and get released in the form of CO2 gas. Okay. So, these reactions that we are going to write. Okay. What is happening, what is whether it is moving in the right direction or whether it is moving in this direction, given the prevailing temperature, given the prevailing pressure, okay, given the prevailing chemical composition, given the pH of the system, all other parameters, we have to start understanding what is the stage of saturation, stage of equilibrium, whether depth is causing the solubility related changes or not. So, these questions has been understood using thermodynamics. In fact, a lot of our thermodynamic understanding has come from the oceanic oceanic studies in the past. Okay. Chemical oceanography, okay, which started almost 50 to 100 years ago, okay, that formed a lot of foundation to aquatic geochemistry. Now, given these kinds of examples, okay, we are going to understand the application of thermodynamics in aqueous chemistry. So, again as I have broadly again repeatedly trying to make you understand is that first thing that we are trying to calculate is the chemical distributions at equilibrium, what reactions are happening, okay, what is the distribution that is happening at equilibrium, if it is a non-equilibrium state, what is happening, like that, okay, and the potential for a given reaction to occur. That is the second thing that we are going to try to understand, okay, that what reactions are likely to occur given this temperature, given this pressure, given this oxidation state, given this organic compound. So, what reactions could happen, okay. So, that we have to calculate, okay, whether it is precipitating, whether it is dissolving, okay, whether it is forming complexes. Okay, so, that kind of understanding we have to develop, and again I will repeat this, that most of the understanding has already been transformed into models, okay, and you can readily find these models in the softwares, okay, such as you will see this software called MINTEQ, okay, MINTEQ. Then there is another software called FreeQC. Okay. There are different softwares available which allows us to calculate these kind of reaction conditions, okay, and they are dependent on certain type of reaction databases. Okay. These reaction databases are there, and there is some kind of speciation modeling, models are also there, and all these kind of modeling softwares, if you want to improve on them, if you want to understand better, we need to understand how they are working. Okay. So, for that we need to go a little deeper into our thermodynamics. Now, the main things that therefore I would like you to understand from this lecture is how we define a equilibrium constant, how we define the free energies, because if the energy is not available, there will be no reaction, right. So, how we are going to do the delta GF0, the delta GF0 is the free energy of formation, that is the standard free energy of formation. Delta GR0, that is delta GR naught, that is called the free energy of reaction at a standard standard state. Then this is just delta GR, that is the delta free energy of a particular reaction. How we calculate K from delta GR naught, and what is the difference between Q, okay, the reaction quotient from equilibrium constant, and how that determines us which direction is the reaction going to proceed. Okay, if you understand these basic concepts, your aquatic you can apply them to understand the natural water compositions. Let us first brush up a few basic concepts in thermodynamics. Okay. First of all, equilibrium, okay, this term thermodynamics, equilibrium or kinetics influence the abundance, distribution and fate of natural substances in the environment. Okay. More importantly, what is naturally possible in nature and what is human induced, okay, that also is extremely important. So, naturally if you are going in any pristine environment, what reactions are happening. Now, as I said, due to some mining activities we have modified that system. Now, what is going to happen? Okay. So, I am repeatedly going on saying this term called system. What is a system? Okay. A system is a group of minerals or atoms or rocks, gases, whatever said inside a given volume or within a boundary that you could define for your convenience. Okay. It can be a mineral grain, it can be a raindrop that you are considering, it can be a particular area of waterlogged soil, it can be a lake system entirely, or it can be an entire aquifer which can spread across many kilometers. So, your system you are going to define, and it can be of two type. It can be open type, that means it is continuously exchanging both energy and matter with the surrounding. For example, if you are considering a lake system, it is continuously exchanging matter and energy, okay. Or you can say that it is closed with terms of matter and it is exchanging only in terms of energy. For example, you consider only a mineral grain. So, you are only exchanging energy, but matter remains same and it is a closed system. Okay. Or you artificially consider it as a closed system and you say it is not exchanging any matter, whatever is there, it is there in the system, only energy is getting exchanged. So, you can assume of certain situations as well. Okay. Also, not necessarily all the parameters act in the same way. Okay. For example, I have given that a system can remain open for certain parameters, but can behave as a closed system for certain other parameters. For example, a ferric iron present in oxide minerals, okay, in an aerated soil will generally be immobile. Okay. As I have said, that ferric iron, the ferric state of iron Fe3 plus, that is less soluble and therefore less mobile. Okay. In which case any volume of the soil is a closed system with respect to the ferric iron, but there is other exchanges going on in that soil such as gases, okay, carbon dioxide, oxygen, those gases are getting exchanged, right. But in terms of the volume of soil, specifically with respect to the iron content, that is a closed system, that is no iron is getting lost from that system. So, there is no matter exchange, but other components such as gases, oxygen and carbon dioxide, that can get exchanged. Okay. Phases. What are phases? It is a chemically and physically homogeneous state, okay, and that is characterized by constant pressure, temperature, volume and composition. Okay. It can be gas, liquid, solid, plasma, okay, multiple phases can be existing. Now, the number of phases that can coexist at a equilibrium condition is given by this Gibbs phase rule. Okay. Gibbs phase rule that states that the degree of freedom of the variables that you have is equal to the number of components minus the number of phases plus 2. Okay. So, if you are having a, if you are plotting temperature and you are plotting pressure, we will see multiple times, you will see that there will be stability of certain, this can be a particular phase which is A, this can be a particular phase B, this can be a particular phase C, right. So, how many degrees of freedom does this region has, okay, that you can calculate from the number of components minus the phases that is there plus 2, okay, that is the equation that you are going to use. Now, just brushing up on the thermodynamic laws, because from here we are going to derive certain equations. Okay. So, the 0th law says that if two systems are in thermal equilibrium with the third system, then there is a thermal equilibrium with each other. For example, if A and B are at thermal equilibrium, that is heat exchange is same in both directions, and similarly A and C is also in thermal equilibrium with each other. That means that B and C should also be at thermal equilibrium with each other. Okay. Again I repeat, if A and B are in thermal equilibrium and A is also thermal equilibrium with C, then B and C are in thermal equilibrium with each other. That is the 0th law of thermodynamics. The first law of thermodynamics, the most easiest to understand, is the law of conservation of energy. That means energy can neither be created nor can it be destroyed, it can just be converted from one form to another. And this gives us the internal energy formula, that is internal energy E is equal to dq minus dw. That is the internal energy of a particular system depends on the heat, that is a change in dq, heat content minus the work done by the system. This is subtracting the energy, right. The system is doing some work. So, therefore, the sign here is minus. If the system would have received a work, then it should have been dq plus dw. So, this is doing work, doing some positive work, and here work is done on this system, is receiving some work. Okay. And internal energy is a state function. What is a state? Do you understand this differences? State function and there is another called the path function. Okay. State function means that that particular parameter just depends on the first and the last state. It does not depend on the path that has reached to take that to state. Okay. There are certain other opposite functions which is called the path functions. For example, work is a path function, and that means that the work depends on the displacement path and not the initial and the final position. Okay. So, internal energy is a state function and is equal to dq, that is the heat energy, and if it is doing some work then it is minus dw, the work done, or if it is receiving some work then it should be equal to dq plus dw, that is the work done on that particular system. The second law of thermodynamics says that the entropy of a system is not in thermal equilibrium, increases. Okay. Entropy is a measure of the randomness or disorder of a thermodynamic system. As the entropy increases, less energy is available for useful work. So, we are all moving towards this randomness. So, entropy is basically a kind of randomness. Okay. So, every thing, if it is left over, it will move towards its most random state. Okay. Entropy S is a function, is a state function, and that can be written as this. So, ds is greater than dq by t, that is a state function. And spontaneous processes are irreversible in nature. For example, consider this is a block of ice. Okay. Now, if you just leave that block of ice, it will start melting. Okay. Now, from here to here, the entropy has increased, okay, because here there was more structure. Okay. The ice had a particular structure, there was a particular bonding and all that. Okay. Now, if you just leave that ice, it will form a puddle of water, right. So, it will move from the most structured state to a not so structured state, right. It will move from a solid to a liquid form, and therefore, this is a very spontaneous process, but this is not a spontaneous process. To do that, you have to do work on that water, you have to chill it to make it back to a block of ice. Okay. And all closed systems tend towards moving to an equilibrium, in which the entropy is at a maximum state and there is no energy available to do useful work, right. So, all all reactions are moving to work, are moving such that the entropy increases and no energy is available to do any useful work. Okay. Third law of thermodynamics, that states that when the temperature approaches absolute 0, entropy approaches 0, and that means in practical terms it means that it is very difficult to attain absolute 0, because as we are taking out heat from a system, it becomes more and more difficult to take out heat. Okay. If you are trying to cool something, if you are trying to chill something, okay, as the temperature is getting lowered, it becomes more and more difficult to reduce its temperature. So, it is almost practically impossible to attain absolute 0, although theoretically possible, but practically it gets an extremely difficult situation. Now, after this basics, laws and all that, what we are trying to understand is what is free energy and how do we relate all the thermodynamic laws to it. Okay. Because as we have said that our objective is to understand whether a reaction is possible or not, whether a reaction is spontaneous or not. Okay. And that the free energy will gives us this idea whether the reaction is possible or not. Okay. Now, the theory of thermodynamics, if I am just giving a very brief this thing, is therefore represented by 5 fundamental variables, that is temperature, pressure, entropy, volume and number of components. Okay. The compositional variability. Compositional variability is denoted by Ni. There are 2 modes of energy transfer. One is through heat heat is represented by small q, and there is work, that is W. There is one characteristic state function, that is E, which is the internal energy of the system on which everything is going to work on. Okay. In addition to that internal energy, there are three additional energies that we are going to talk about. The first is the enthalpy. Okay. Enthalpy is the total heat in the system. Okay. Therefore, enthalpy, which is represented by H, is equal to the internal energy plus pressure PV. Okay. That is the work done on it. Okay. Another form of expression is the Helmholtz free energy, and that is represented by A, which is equal to E minus Ts. Okay. And finally, it is the Gibbs free energy, that is represented by G, which is equal to H minus Ts. Okay. So, in our next lecture, we are going to talk more about our Gibbs free energy, and we are going to talk about all the other kinds of the delta Gf0, delta Gr0, delta Gr, writing the chemical equilibrium, how to write K, all these in our next lecture. How we are going to calculate this, we are going to see in our next lecture. Okay. So, with this we come to an end to this lecture. See you in the next class.